All right, so here's the answer key for the stoichiometry practice problems. The first three problems are straight mass to mass stoichiometry conversions. And then we start to introduce some of the percent yield concept for the next couple problems. And then the final problem includes limiting reactant, grams to moles, moles to grams, and a percent yield, all in one complete problem. So let's start. We have this reaction between lithium hydroxide and hydrobromic acid. The question is, if we start with 10 grams of lithium hydroxide, how much lithium bromide will be produced? So we have to assume in these problems where we only get one reactant that we have excess of the other reactants. So that's not going to run out before we use up our 10 grams. That's just implied and assumed anytime you only have one reactant. So the 10 grams we're given. We have to divide that by the molar mass of lithium hydroxide, which is 24 grams. And you would find this using the periodic table, which is on each page in the Classic version. I'm just going to include the numbers here rather than trying to squeeze the periodic table on here as well. So you add the mass of lithium, oxygen, and hydrogen together off the periodic table, and you get 24. So 10 divided by 24 equals 0.42 moles. Here's another thing that I like to do sometimes with these, to just kind of keep in my head straight what I'm working with. So this is lithium hydroxide. That's what I was given. This is also lithium hydroxide, and I converted it to moles of lithium hydroxide. In the mole ratio, this is where things flip, and we transition from what we were given to what we are trying to find. And from this point to the end, everything that I'm working with is in reference to the product that I'm trying to solve for, the lithium bromide. So again, that's something that might help to keep track of where we're getting these numbers and why we're putting them where we are. Also, keeping in mind that we're starting with one thing and we're converting it into something else by way of the chemical reaction and the chemical equation. All right, so 0.42 moles of lithium hydroxide. The mole ratio always comes from the chemical reaction, chemical equation. All of the coefficients in this equation are 1, so that makes this really simple. There's 1 mole of lithium bromide for every 1 mole of lithium hydroxide. Or to look at it the other way around, for every 1 mole of lithium hydroxide you use, you'll produce 1 mole of lithium bromide. So that makes this conversion 1 over 1. So 0.42 times 1 over 1 is 0.42 moles. The difference here is what we've now done is we've said if we had 0.42 moles of lithium hydroxide and we put it through the reaction, we should get 0.42 moles of lithium bromide. So we've switched over from reactant to product at this point. And then to find the answer in grams, we take the number of moles, which is 0.42, times the mass of lithium bromide, which again, this number comes from the periodic table. Add the mass of lithium to the mass of bromine, and you get 87. 0.42 times 87 is 36.5 grams. And that is the answer to the question, how many grams would you get? 36.5. Next question. Here we have some different coefficients to work with, so we'll have to figure out what the ratio is going to be. But we're starting with, and it says, if you start with 45 grams of ethylene. So let's label our substances here. The first 2 boxes are our reactant, which is the ethylene. The center box, or the ratio in the middle here, is the transition between what we're starting with and what we want to end up with. How many grams of carbon dioxide? So carbon dioxide is our unknown. That's what we're solving for. So everything from that point on has to do with carbon dioxide. We had 45 grams we were given. The molar mass from the periodic table of 2 carbons and 4 hydrogens would be 28 grams. So here we actually have more than a mole. In the last one we had about half a mole. So 45 divided by 28 means we have 1.61 moles of ethylene. And the reason we have to do the moles here, the grams to moles conversion, is because the equation is always expressed in terms of moles. So I can't just plug the grams in and use the equation to figure out what I'm going to get. I have to convert everything to moles because that's where the ratio in the coefficients comes from. So now that I have this in moles, 1.61 moles of ethylene, the ratio, CO2, is here. It has a coefficient of 2. So that means I will produce 2 moles of CO2. Ethylene doesn't have a coefficient, so that's 1 mole. Okay, so for every 1 mole of ethylene, I will produce 2 moles of CO2. So 1.61 times 2 over 1 is 3.22 moles. We've now established that with the 1.61 moles of ethylene, I will produce 3.22 moles of CO2. The proportion is 2 to 1, so twice as many moles of CO2. To get to the answer, which is grams, how many grams, and multiply that by the molar mass of CO2, a carbon plus 2 oxygens off the periodic table is 44 grams. 3.22 times 44 is 141.7 grams of CO2 would be produced by that reaction. All right, third one, again, another grams to grams stoichiometry problem. We're starting with 20 grams of HCl. So HCl is our given, goes top, top, bottom. And then we're trying to figure out how much H2SO4 would be produced. Okay, so from the mole ratio on, all the numbers are in reference to H2SO4. Okay, given 20 grams, the molar mass of hydrochloric acid, a hydrogen and a chlorine, is 36.5 grams. If we divide those, we get 0.55. The ratio, again, always comes from the equation. In order to produce one, the coefficient is 1 mole of H2SO4, we need 2 moles of HCl. So it's a 1 to 2 ratio, or a half. So half of 0.55 is 0.275 moles of H2SO4. So now we've switched over from the reactant to the product. 0.275 moles of H2SO4 will be produced. The molar mass of H2SO4, 2 hydrogens, a sulfur, and 4 oxygens, is 98 grams off the periodic table. 0.275 times the 98 is 26.95 grams of H2SO4. That is the answer to that question. All right, so the next one, we're back to an equation with all 1 coefficients, so that's kind of nice. But we're adding in a question about percent yield. So all of the answers we've gotten so far to the grams to grams, or it would be true also of moles to moles, but we're doing gram to gram conversions. All of the answers, the numbers that we get over here in this last box, those are called theoretical yield. We haven't called it that in these problems yet because we aren't doing anything other than trying to find it. But now that we want to find a percentage, we need to know the theoretical yield, which is what the boxes will tell us, and then also the actual yield, which is given to us down here. So we have to do that at the end. First, we need to calculate the theoretical yield based on the information we're given. We're beginning with 20 grams of lithium hydroxide. 20 grams, this is lithium hydroxide. This will be moles of lithium hydroxide. Down here is the coefficient of lithium hydroxide, and we're trying to find lithium chloride. So that's our our unknown, our answer is going to be in terms of lithium chloride. So we'll just label these boxes. Okay, now plug in. Lithium hydroxide has a molar mass of 24 grams, which means 20 grams divided by 24 is 0.083 moles of lithium hydroxide. The ratios, again, in the equation, every single coefficient is 1. So that makes this a very easy conversion because we're doing 0.83 times 1, which is 0.83. Again, the difference here is now we have converted the number of moles of lithium hydroxide that we used to the number of moles of lithium chloride we will receive, which is 0.83. And then we multiply that by molar mass, which is 42.5. And we get a molar, not a molar mass, we get a product in grams of 35.28 grams. Okay, so that's the answer to the first part of the question. And then the second question says, I actually get 6 grams, what's my percent yield? This number, again, this number is the theoretical yield. So in order to find percent yield, we take actual divided by theoretical. So what did we actually get? Divided by what we could have gotten. What's the maximum? And then to make it a percentage, I sometimes leave this step out, but you multiply that because this will be a decimal. You multiply it by 100 to make it a percentage, and we come up with a number of 17%. So not a great percentage, but that is what it is. It can be anything up to from 0 to 100%, between 0 and 100%. It shouldn't be 0, and it shouldn't be more than 100. But anything in between is fair game. Okay, here's a slightly different variation on the percent yield question. Let's find the theoretical yield first. Again, the theoretical yield is just what we get when we do the calculation. So it's not labeled that on this box, and we haven't described it as that in the first few problems, but the answers we've gotten to all of those problems at the beginning were the theoretical yields in those cases. So let's go back. We have 5 grams of propane, C3H8, C3H8. The bottom here is going to be the C3H8. And we want to know water. That's our goal, is to figure out how much water we're going to produce. H2O, 5 grams of propane. Propane has a mass of 44 grams. Divide that, we find 0.11 moles. So 5 grams of propane is 0.11 moles of propane. The mole ratio, we're looking at water versus propane. And again, these are moles. That's the unit here. So 0.11 times 4 over 1 is 0.44 moles. So for every 0.11 mole of propane we use, we get 0.44 moles of water, 4-to-1 ratio. And then we multiply that by the molar mass of water, which is 18. 0.44 times 18 is 7.92 grams. So that is the theoretical yield. Now the question doesn't ask us what the percent yield is, given an actual amount. It says, if my percent is 75, what was my actual yield? So we can set this up, right? Since actual divided by theoretical times 100 equals percent, we can just plug in, and we are going to solve in this case for the x. So this is really x over 7.92 equals 0.75. Then we would cross multiply, and we would find that the actual yield is 5.94 grams. Okay, and depending on how comfortable you are with percentages, really what you're doing is you're multiplying the 7.92 times 75%, and that's how you get the answer. So this is the answer to the second part of the question. The theoretical yield question comes from the box at the end of the equation. All right, one more percent yield question, and then we're going to do one big problem that ties it all together. How many grams of hydrogen will be produced? So hydrogen, which is H2, this time they gave us the unknown first instead of saying if you start with. I'm just wording the question differently. Given 100 grams of beryllium. Okay, so we have 100 grams of beryllium to start. Beryllium has a mass of 9. So 100 divided by 9 is, that's grams, 11.1 moles of beryllium. In the equation, both of those coefficients are 1 mole, 1 mole of beryllium. So 11.1 times 1 is 11.1 moles. So if we react 11.1 moles of beryllium, we should get 11.1 moles of hydrogen. Molar mass of hydrogen gas, H2, is 2 grams. So that means we're going to get 22.2 grams of hydrogen. There's your theoretical yield. That's the answer to the first part of the question. The second part of the question is if the actual yield was 4.5, so actual is 4.5 grams over 22.2, okay, times 100, you get 20.3%. Okay, so the percent yield is 20.3. Theoretical yield was 22.2 if you start with 100 grams of beryllium. All right, so the last question, kind of have to space this out because it's going to take a little bit of work because it's got a bunch of stuff wrapped in here. So here's the reaction. And again, a lot of this wording up in the word problem is just describing what's happening. There's no information in that first paragraph that we're going to directly use in the solving of the problem. So the equation obviously is very important. Balanced equation, you have to have that. How much SO2 can be produced? So that's going to be our unknown. From 25, that should say of, 25 grams of Na2SO3 and 22 grams of HCl. So here's the first time that we're given two reactants. In this case, it's both. There's only two. So we're given both reactants to work with, and we're asked to figure out how much of a particular product we're going to get. So we can't just assume that, oh, well, the number that's smaller is going to run out first. It doesn't work that way. Sometimes it does, but you can't count on that. So we're going to have to do some calculating to figure out which one of these reactants runs out first and is therefore the limiting reactant. So we have two different calculations that we're going to perform. We're going to run the numbers once with Na2SO3, and then we're going to run them again with HCl. Both times we're working on the same product. Okay, so I'm going to label these just like we did before, except it's going to get a little crowded in the middle here. So this is Na2SO3. This is, I'm going to put it in here, Na2SO3. This is HCl. And this is SO2. So we're doing a mass-to-mass stoichiometry problem twice. Same product, two different reactants. Okay? And then we'll figure out which reactant gives us the smaller amount of product. That will determine our theoretical yield. So let's take a look. 25 grams of Na2SO4. The molar mass of Na2SO4 is 126. Again, 2 sodiums plus a sulfur plus 3 oxygens gives you 126 grams. We're also going to use 22 grams of HCl, hydrochloric acid, which has a molar mass of 36.5 grams. Now you could run these completely through one by one, do the top one first, then go start to do the bottom one. I prefer to do them kind of in parallel because once I get to the mole box here, I can actually stop one of the calculations because once I get to the mole box, the first one after the mole ratio, that number will tell me which one is going to be the limiting reactant. So we'll get to that in just a second. Okay, so 25 divided by 126 is 0.198 moles. 22 divided by 36 is 0.6 moles. Right, now the mole ratio. SO2 is the product in question here in both. So 1 mole, that's the coefficient in the equation for SO2. On the top row, we're looking at NaSO3, Na2SO3 rather. That is also a 1. For the HCl, it's a 2, 2HCl. Okay, so the mole ratios are different, which can affect which one ends up being the limiting reactant. On the top row, 0.198 times 1 over 1 is 0.198 moles of SO2, and then 0.6 times 1 over 2, or 0.6 divided by 2, is 0.3 moles of SO2. All right, so here I can see that the 25 grams of Na2SO3 would produce 0.198, just about 0.2 moles of SO2. The 22 grams of HCl would actually be able to produce 0.3 moles. So again, the smaller number that we started with actually yields more product. And it has to do with the ratio and the molar mass and things like that. So you can't just assume the smaller amount you start with is going to give you the smaller amount that you end up with. Okay, since both of these boxes here are the molar mass of SO2, whatever number I have in the mole box here, they're going to be multiplied by the same thing. So this is where I'm saying at this point, I can see that this number is smaller, and it's still going to be smaller if I multiplied it out. So I don't have to do this calculation. I've now determined that this top row is going to be the answer because that produces the smaller amount. Again, what does that mean? The limiting reactant here, it means that yes, if I had HCl and a whole bunch of Na2SO3, I could produce 3.3 moles of SO2. But I don't have enough extra, or I don't have any extra Na2SO3. The amount of Na2SO3 I have will only produce 0.2 moles of SO2. So once I get to 0.2 moles, even though I have more HCl, I can't use it. Okay, so there's going to be excess of that hydrochloric acid. We call it the excess reactant. The Na2SO3 here is going to be the limiting reactant because it runs out. Okay, so if we do the 0.198 times 64, we get 12.67 grams. And again, if you did the bottom number, you'd come up with something around 19. And so you'd see that you get less here. Okay, so the limiting reactant is the Na2SO3, which means the answer to the question, how much can you get? You can get 12.67. If you had more, if you had plenty and plenty of that Na2SO3, you could get more. You could get 19 grams with that amount of HCl, but we don't have enough Na2SO3 to get there. So that's the answer to the first question. The limiting reactant we said was Na2SO3. The reaction actually produces 10 grams. We said the theoretical was 12.67. So actual over theoretical, and then it would be times 100. Times 100, I keep wanting to do equals, is 78.9% yield. Okay, so that problem brought in everything. We've got mass to mass conversions, stoichiometry rather, mass to mole, mole to mass. a mass-to-mass stoichiometry problem. We had to do it twice because we didn't know what the limiting reactant was. We were given 2 reactants to work with. So that's why we did this twice, to identify the limiting reactant and the theoretical yield. So we get both of those from this process. And then the final piece was, what's the percent yield? So the theoretical is what we got on the last slide. This number was given. We determined that as a percentage. We get 78.9%. Okay, so that is the answer key for this first round of stoichiometry practice problems.